Hey everybody, in this video we'll be looking further into how to program neural networks. More specifically, we'll be looking into how to program convolutional neural networks, and we'll also be recapping how to program linear neural networks. Now of course this is the second programming video in the series, so make sure to watch that one before this, as well as all the other theory videos before this in the series, so you have proper context. So, we'll first begin by looking over the x greater than y program that we covered in the first programming video. This here is the x greater than y program in its entirety. This is the simplest version where it simply trains the model and then allows the user to input two numbers, and then it'll make a single prediction based on those inputs. Just as a reminder, the model that we're training is used to determine which of two numbers is greater. So let's just go through a quick recap of this code. Of course, the full explanation is covered in the first programming video of the series. So at the top, of course, we have our libraries. And for our programs, we're using the PyTorch libraries. So we have import torch to use that. And then below that, we define our structure of our neural network. You can see here, this is where we define the structure of each individual layer, specifically how many inputs each layer will have and how many neurons it will have. And then below that, in the forward function, we're basically telling how we want our inputs to pass through the neural network. In what order should it go through the layers? And we also define what nonlinear functions should be applied to the outputs of each layer. Going down, we have our data creation functions. This is something I said in the last video, but normally you wouldn't create your own data, or typically you wouldn't. You would find it from some data set elsewhere, usually online. And then here we have, in our main function, you can see we define our model, net, as well as the optimizer that we want to use. We call our data making function, and then we begin the main training loop. So you can see this is here where we take our training data and we package it properly into tensors so that it can be used by the neural network. Of course, PyTorch requires that all data that is going through and handled in neural networks must be in the form of tensors. And then here is the actual main training loop. We pass our data into the neural network, we apply a loss function, we perform backpropagation, and then we use our optimizer to adjust the weights of our neural network. So at the bottom here is where we do our actual prediction. And you can see right over here, this is where we take our input data and we actually put it into tensors. Above that is where the user gives input, of course. And then here's actually where we first pass our input into the neural network, and it will make a prediction which we store as output, and then we interpret that prediction here, and then the program will make a relevant output. So what that actually looks like, well, let's run the program to see. So if I run the program, it'll take a little bit to first train the model. All right. So now I can actually input two numbers. Let's say I input 3 and 4. And now the model makes a prediction, and it correctly states that our second number, y, which is 4, is in fact greater than the first number, x, which is 3. So now we'll go over a set of programs that will use a convolutional neural network. We'll be creating a model that will be able to classify images of triangles and squares, similar to the example that we looked at in the convolutional neural network theory video, which was the previous video in the series. The first couple programs that we'll be looking at will be responsible for creating the necessary data to train and make predictions with our convolutional neural network. Here I first have the program that we'll use to create the set of data that we'll use for making predictions with our AI model. So what this program will actually do is it will create 50 random images that will either be squares or triangles. And it will store them in a folder that I've named predict, so we could use them for later. Now this folder predict will have two subfolders, S1 and S2. Images of squares will go into the folder S1, and images of triangles will go into the folder S2. So let's take just a quick look at the program. Of course, this is not the main focus of the video, but we'll still cover it quickly. So this function I have defined here, this will just make sure that our folders are fully clear before we put any new images in them. And then you could see we have this function, generate bulk images, which is just the function that we'll use to actually create all our images. Something to note, you can see that we have this variable, or rather parameter count. This is just how many images we want to create. When we call this function below, we'll call this with a count of 50. Here, this line of code, this is where we will randomly pick between either a square or a triangle. We refer to it by the folder, the corresponding folder, S1 or S2. And then here's the actual set of instructions, or the code, that we will use to create the images. So you can see this is where we create a random square. And of course, with this program, you can see we're actually not going to be creating the exact same square image each time. We're going to be creating squares with different sizes and different positions along the entire image. And this will allow us to really properly test the capabilities of our model. So here, this is the section for creating square. And you can see that we do in fact save it in this folder S1. And below, this is the logic for creating our images of a triangle. And you can see at the bottom, we save it into the folder S2. Again, you don't need to worry about this too much. but you can see down here, we actually call our function, and you can see we call with a count of 50, so we create 50 images. Now here's the program that we'll use to actually generate the set of training images for our AI model. The one before, remember, was the images used to test the accuracy of our predictions of our model. So if you actually look through the program, it's pretty much the same as the last one, just with one big difference, really, and that's the file that we'll be saving the images to. Instead of saving it to the predict folder, we're saving it to this folder I've named train, which will have two subfolders, square and triangle. Of course, images of square will be saved to the square subfolder, and you can see down here, images of triangles will be saved to the triangle subfolder. And of course, when it comes to actually creating the images, again, we're creating the squares and triangles in such a way so that none of the images will actually be the same. They'll all have squares and triangles with different sizes and different positions. So now we'll go over the program that will actually be responsible for creating our AI model, training it, and saving it. Here is the program that we'll be using for creating and training our AI model. You might immediately see that there are a couple of things similar to the x greater than y program from earlier. Indeed, a lot of it is pretty similar. Let's go through the program step by step. So, looking at the libraries, like the x greater than y program, we're of course going to be using the PyTorch library, which is up here. But you can see we also import datasets, transforms, and data loader. And what we'll be using these for is just to handle our training and predicting data, which we created in the two earlier programs. It will allow us to import our images into the program and modify them in a way that our neural network will be able to handle. So going down, here this is one of the most important parts of the video, because this is where we actually see how we can create the structure of our own convolutional neural networks. So, the first couple lines are the exact same as defining any other neural network. But here you can see, this is new. Here we decided, instead of defining each individual layer one at a time and then having to set what nonlinear activation functions we use in our forward function, we are going to instead define self.features, and this will handle the entire convolutional part of our neural network, including all CNN layers, all nonlinear functions that will be applied to each CNN layer, and all of the pooling functions. So here this method conv2d, this is where we define a single CNN layer. We see that we have a few parameters. The first parameter is the number of inputs that we have, or number of channels that we have. And we have it to 3 because even though we're dealing with black and white images, the images that we have are still going to be in RGB. Next we have 8, this number 8, which corresponds to the number of outputs that this layer will have. What I mean by outputs? Well, if you remember, each filter in a CNN will actually give an entire matrix as an output, so we're basically saying that we'll have 8 output matrices, or rather that we'll have 8 filters. And then here we also define the kernel size. Kernel is just another word for filter, so we're basically saying we want filters which are 7 by 7 pixels. And then padding, this will just add 3 pixels of empty space to our images. And this will allow us to have images which are, or rather outputs, which are the exact same sizes as the original input images. Below that, you can see here we also define our nonlinear activation function, the ReLU function, as well as our pooling function. We're using this maxPool2D. This will basically just take 2 by 2 sections, as instructed by the parameters, of our images, our output matrices, and it will return only the greatest value of these 2 by 2 sections. And we'll do that for the entire image and basically create a new, smaller matrix. And again, here now we have a second CNN layer. This time we'll be having 8 inputs, because remember, number of outputs that we have from the first layer will be equal to the number of inputs for the second layer. Again, each input's going to be sort of like an image, or rather it's going to be more correctly to say a matrix. And then this time we'll have 16 outputs, or 16 output matrices. We use this time, again, the same filter size and same amount of padding. Now below that, here we're actually just defining a set of linear layers or fully connected layers, because as you might remember from the previous video about CNNs, we can use convolutional layers to try and determine the filters that can be best used to classify images. But to actually do the classifying, we'll also need some fully connected layers to do that as well. And this is where we define them with the code that we saw, same kind of code that we saw in the x greater than y program. You can see that the number of inputs for our first layer is going to be 16 by 16 by 16, or 16 times 16 times 16. This is because after we do the pooling, our images will be shrunken down to 16 by 16, and we'll have 16 of them. Again, you could see from the output of the previous layer. So then now, in our forward function, here's the forward function. Again, this simply defines or describes how the inputs that we give into our neural network will go through our neural network. So they'll first be passed through this dot features, self dot features, which we defined above. This will be all our convolutional layers, all our pooling functions. Then we actually, below that, have this command. We have this command dot view, and what this will do is it will take all our output matrices, and then it will basically just flatten it down to a one-dimensional tensor. Because remember, our linear layers, they can't take a matrix as an input. They have to just take pretty much a list of values. So here is just a visual representation of the neural network that we created. We can take a look at the individual layers. So we first start with our inputs, which will be 64 by 64 images. Again, we have 3 for RGB. We perform convolution, and we'll get an output of, or rather we'll get 8 output matrices, which again will be the same size because we'll apply a padding of 3 to each side of our input. We then apply the maxPool function to decrease the size of our matrices and allow us to find different levels of features. So you can see we go from 64 by 64 to 32 by 32. So again, we'll have 8 images now, or 8 matrices, and we'll do convolution once more. We'll pass through convolutional layer, and we will get 16 outputs. And again, we perform max pooling one more time, and this will decrease the size of the images to 16 by 16. And then we'll pass it into our fully connected layers. You can see we'll actually have a total of 4,096 inputs, which again, this is how many we get when we flatten the 16 by 16 images into this single list. And we'll have 2 linear layers. We'll first have a linear layer which will have 128 neurons, and then the outputs from those neurons will be connected to a second linear layer which will only have 2 neurons. And then that will give 2 outputs, and from those 2 outputs we can make our classification. So now going back to the program, let's see how the training is actually done, the training of our model. So the first thing that we do is we, of course, actually get our training data into the program, and we do that over here. So we first use this data sets that we import. We use that to get our files into the program, so we can of course train with them. You could see in the parameter of this method image folder, we set train as the file we want to extract the images from, and then we use this data loader, and this will basically just format the images into batches. And you could see at the end we also have this shuffle equals true, and this basically means that every time we run a epoch or a training iteration, it will randomize the order of the images in the batches, and this will prevent overfitting. Now you could also see that in the where we load in the images with datasets, we also say transform equals transform. Well, this is referring to, up here we're using again transforms, which we imported earlier, and what this will do is it will just make sure that, or it'll turn all the images into a format that our neural network can handle. So first dot resize, this will just make sure our image is 64 by 64. It will then turn it into a tensor, and then it will make sure that all the values of that tensor are between 0 and 1. That's what dot normalize does. Now, looking below, here we just set model equal to shape CNN. This is the neural network class that we created earlier with the structure that we wanted, that we defined. Below that, we define our loss function. We're going to be using the cross entropy loss function. And below that, we define our optimizer. So now going into the main training loop, we can see that when we use the data loader to format our training data into batches, it actually automatically assigned each image a label, which it got from which subfolder it found each image in. So it'll either have a label of square or triangle. And now here, of course, this is where we do the actual training. It's pretty much the exact same as the x greater than y program. We first pass our inputs or our images into the model. It makes a prediction. From that prediction, we then apply that to a loss function as long as the as well as the labels from earlier, which the labels would be the correct output that we expect. And then the .0 grad that just resets all of the gradients to prevent them from accumulating a larger and larger change from each iteration. And then we apply backwards propagation to calculate the gradients of all of the weights of our neural network. And then finally, we simply adjust all the weights. This is the exact same training loop that we've covered pretty much all of the videos. And then the only other important thing we really need to see here is this is the line that allows us to save our model. Here we're just saving it into this file that I've named model. And now if we can run this program and we'll see here the progress of the training, and we can see the loss being printed over each epoch, and we see we get pretty much to nearly 0. And now finally we'll be going over the program which will load the model that we've just trained and then make predictions based off of the predicting data that we created in the first program. And now we'll be able to see its accuracy. Here is the program that we'll be using to load our trained model and make some predictions with it with the predicting data from earlier. So here, this section, this is basically just, again, defining our own neural network class with the structure that we want. It's the exact same from the program before. In fact, it must be the exact same for it to work properly. And now we have this function that we defined, predict subfolders. This is where we're actually going to be performing our prediction and loading in our prediction data. These parameters, these are just the folders that we want to access. Base path is our predict folder, subfolders is S1 and S2, and model path in our case is model. You can name them whatever you want. Here, we're just setting this variable model to be the neural network class that we defined earlier. We're checking to see if the folder with our model exists in this piece of code. And here we're actually, this is the line of code that's going to be loading in our trained model, which is actually just a set of weights pretty much. Model.eval basically just puts our model into a mode where it won't track gradients. Here again, this is where we define how we want to transform our images. This is the exact same from the previous program. And it basically just turns our images into tensors, which can be passed through into our neural network. Classes, this is just a list that we'll use later for a prediction, and valid extensions is just a list pretty much of the valid file types that we could accept. So now here I have this section, and this will basically loop through our subfolders, and it will make sure that we can access all of the subfolders properly, and it will make sure that whenever we access an image, we're accessing it with one of those valid image file extensions for example, like .png or .jpg. Here, this is where we actually extract an image, and you can see we apply our transformations here, and we also unsqueeze it. You could see this basically just adds one extra dimension to our image tensor, as our neural network still expects a dimension for which would represent the size of a batch, even though that would just be one for us. And now here, this is where we actually make our prediction. We first pass our image into our neural network, and then from our output, we'll take the index of the output of the highest value, and based on which value is higher, the index of that value will then correspond to that classes list from earlier. You can see in this line specifically, the value of prediction will either be square or triangle based on which of our outputs is higher. All right, and where we make our distinction here based on the output, will either, if it does match the corresponding folder, then it will be considered a match. Otherwise, it won't be. This will make sense when I run the program. So let me do that right now, actually. All right, so we can see that I ran the program, and here we have a table pretty much where it just printed what folder we're accessing from and the file name for each image, and then it will either print 1 or 0. If it's 1, that means we did have a match and we made a correct prediction, or rather the model made a correct prediction, and if it's 0, that means the model made an incorrect prediction. So you can see we're first accessing from the folder S1. If you remember, S1 contains squares. And then we access from the folder S2, which contains triangles. And at the bottom, we've also just included how accurate the model is. And we can see that it was able to guess 48 images correctly, which is a 96% success rate. And now that concludes the second video on programming neural networks. Thank you for watching.